So I came across this equation in the Griffiths quantum mechanics book, which most undergraduate physics majors read. And I didn't know where it came from, so I decided to find out. So this is the potential energy between two particles in a hydrogen atom, and those two particles are a proton and an electron, and I imagined them to be centered at points, and I called them point A and point B. Point B is the electron, point A is the proton, and I drew an origin so that R is the vector from the origin to the proton, and R sub k is the vector from the origin to the electron. Okay? So the Griffiths textbook hinted that this equation comes from Coulomb's law, but I didn't know what Coulomb's law really was mathematically, so I looked it up in my electromagnetism textbook and found this equation. Blah. It's pretty nasty, but for hydrogen, it's not so bad, because n equals 1. What is n? N is how many other, keyword other, charges there are besides the one you're thinking about, which is Q, because you're trying to find the potential energy of Q. And Q, according to this diagram, is the proton. So really, we're finding the potential energy of this proton due to the presence of this electron. Okay? So n equals 1, because there's one other charge besides Q. So we can get rid of the sum because k equals 1. And F equals 1 over 4 pi epsilon naught. Epsilon naught, by the way, is the permittivity of, the electric permittivity of free space. And this is just the same equation written again without the sum. And I rewrote it a different way because I had no idea what that fraction meant, so I wanted to figure it out. I separated the vector, and I noticed that this seemed like some kind of normalization, so really this quantity here, r minus rk, that's really the distance from, or the vector pointing from point B to point A. And so the length of that vector, or the absolute value of that vector, is just the length. So really this is just indicating the axis along which the force points. The direction of it will be indicated later by whatever sign pops out of this expression. And so I'm going to call this axis f hat, which in this case happens to be negative I. How do I know this? Because of geometry and how I set up the coordinate system and do vector addition to see which direction this r minus rk vector points. And again, rk is the vector pointing from the origin to point B. And all that's left is 1 over the magnitude of that vector squared. But we can simplify this further because we know what this quantity is. It's really just the length of the vector pointing from point A to point B. So as long as that quantity doesn't change with respect to time or space, we can call it r squared. So I'm going to call it r squared. So now this expression right here, using f hat and r squared, becomes negative. Oh, also I substituted the value of the charge and noting that the electron's negative, so there's a negative sign here. So negative e squared f hat over 4 pi epsilon naught r squared. And since we know, based on geometry, the direction of f hat, or the value of f hat, it's negative I. So plug a negative I into this expression, get 1 over 4 pi epsilon naught e squared r squared over I, which is actually just a positive quantity, which means that it points along the direction of I, which is as we expect because unlike charges attract, so the positive charge is feeling a force towards the negative charge, which, you know, makes sense. So this is good. Now, we actually are trying to find the potential energy, so how do we link this force between this proton and the electron with the potential energy? Well, there's an equation also in my electromagnetism textbook, which is, for 3-dimensional cases. It's the force is equal to the negative gradient of the potential energy, where the gradient is really just a vector operator. So whenever you apply this vector operator to a scalar, such as the potential energy, the scalar is just something that isn't a vector, roughly speaking, you get a vector. And in particular, this vector is showing how the scalar is varying in 3-dimensional space. Okay, hence the partial derivatives. But really, since 2 points make a line, we can just consider a 1-dimensional case, and since I chose I as the direction, we'll snag that component off of the gradient and just consider the x direction. So note that the negative still carries over, and this is the equation we need to consider now. So now we kind of need to make an assumption here, because I don't like to integrate partial derivatives. Kind of makes me nervous. So I want to make it into just a normal derivative. So I'm going to assume that v only varies with respect to the x direction, and not time, for instance, so that I know that I don't have to worry about any other variables. It's just x. So if I know that it's only, you know, varying with respect to x, then I don't have to consider any other variances. So then this becomes f equals dv dx, negative dv dxi, and I can multiply both sides by dx to get this equation. And now, starting to get something that can be solved with a bit of integration. So we substitute 1 into 2 first, because even if we integrated this, we wouldn't get very far. So we kind of need some variables in here. So since we already know the force, conveniently, can substitute that force into this expression, and we get this equation here. Whoa, look at that. There are eyes on both sides of the equation. That's awesome. So logically, you can expect that since the directions are equal, the magnitudes must be equal by this equality sign. So let's just equate the magnitudes and, of course, the signs. So everything except for the eyes must be equal. I misspoke when I said magnitude. Probably should have said something like values. Okay. So here I am equating the values, ignoring the unit vector I. And now I'm just integrating both sides. The right side has dv, so integrating from a to b, because that's all we really care about in this problem, assuming that there are no other influences. And using a definite integral is convenient so that we don't have to think about any integration constants. And this is just a physical interpretation, which is really what calculus is all about Anyway, so it doesn't really matter that this isn't super mathematically rigorous because physically I know what's happening. So the total potential energy is the integral, the definite integral from a to b dv. And integrate the other side of this equation as well from the same limits of integration. Over here from a to b. Notice that I took out the constants, but I'm not sure if I can take out this r squared. So I'm going to make some assumptions here. First, I'm assuming that r does not vary with x. In particular, both particles are not moving with respect to each other for an extended period of time or at only one point in time. It does not vary with x then, so can take 1 over r squared out of the integral. And get this quantity here for the potential. And note that this is just r because the sum of all the infinitesimal quantities from a to b is just a finite quantity r. And finally, for substituting, we get this quantity, which is valid for any r not varying along AB, and V only varies along AB. So yeah, that's how you get this expression.